Welcome to this 11th lecture video for Physics 4A. We are starting on a new set of topics and mechanical concepts in this set of lecture videos. We will expand on these ideas fully over the next few sets of lecture videos. In this set, let me start with a reading from the Feynman Lectures on Physics, Volume 1, Chapter 4. This well-regarded classic in undergraduate physics education is now available to read for free from the Caltech website, as you will see when I start reading. If you are thinking, Chapter 4, isn't that awfully early in the Volume 4 energy section? Well, I encourage you to go to the Caltech website and read the Feynman Lectures in context. He has a unique approach that may help you gain a comprehension of physical insights better than the traditional ways in which general physics is taught. In the remaining regular set of lectures, using the example of pendulum, I introduce energy as something that is conserved throughout different mechanical interactions. And I show the Newton's Cradle demo, which we will return to next week after covering the second conserved quantity that we will learn about and use in physics problem solving. And I wrap up these lectures with an emphasis that energy is a calculated quantity and that there are many different forms and formulas for energy. The one common thing binding them together being that the total energy is conserved. Finally, in preparation for what we will cover in the next set of lecture videos, we come back to the topic that we skipped earlier in the semester when we introduced the vectors for this class. We will finally cover the dot product in some depth and show how it will be used as we talk about work and energy. In this and the next set of lecture videos, we are going to start our discussion of conserved quantities, starting with the conservation of energy. And to introduce this part, I wanted to start with a reading from a small section of the Feynman Lectures. The Feynman Lectures are available for free from the Caltech website at www.feynmanlectures.caltech.edu. I'm reading from Chapter 4, Section 4.1. Chapter 4, Conservation of Energy. Section 4.1. What is energy? In this chapter, we begin our more detailed study of the different aspects of physics, having finished our description of things in general. To illustrate the ideas and the kind of reasoning that might be used in theoretical physics, we shall now examine one of the most basic laws of physics, the conservation of energy. There is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through our tricks and calculate the number again, it is the same. Something like the bishop in a chess game on a red square, and after a number of moves, details unknown, it is still on some red square. It is a law of this nature. Since it is an abstract idea, we shall illustrate the meaning of it by an analogy. Imagine a child, perhaps Dennis the Menace, who has blocks which are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully and discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days, until one day there are only 27 blocks. But a little investigating shows that there is one under the rock. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other 2 blocks are found. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation until it is realized that Bruce came to visit, bringing his blocks with him, and he left a few at Dennis's house. After she has disposed of the extra blocks, she closes the window, does not let Bruce in, and then everything is going along all right. Until one time, she counts and finds only 25 blocks. However, there's a box in the room, a toy box, and the mother goes to open the toy box, but the boy says, "No, do not open my toy box," and screams. Mother is not allowed to open the toy box. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces. So she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again and subtracts 16 ounces and divides by 3. She discovers the following equation 4.1. Number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces is constant. There then appear to be some new deviations, but careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water, and she cannot see them because it is so dirty. But she can find out how many blocks are in the water by adding another term to her formula. Since the original height of the water was 6 inches, and each block raises the water by 1/4 of an inch, this new formula would be number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces plus height of water minus 6 inches divided by 1/4 inch is constant. Equation 4.2. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula, a quantity which has to be computed, which always stays the same in her situation. What is the analogy of this to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the first terms in equation 4.1 and equation 4.2, and we find ourselves calculating more or less abstract things. The analogy has the following point. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. Second, the energy has a large number of different forms, and there's a formula for each one. These are gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not that way. However, there are formulas for calculating some numerical quantity. And when we add it all together, it gives 28. Always the same number. It is an abstract thing, in that it does not tell us the mechanism or the reasons for the various formulas. In the remaining lectures, we will go into detail of energy and conservation of energy. I do encourage you to visit www.feynmanlectures.caltech.edu to read the rest of Feynman Lectures. So let me start out with the background for the concept of energy. So where we start from is from an observation that when you look at motion of an object like this bob here, which will be undergoing a pendulum motion, that looking at this makes one think, even before you know anything about tension, force, or the kinematic stuff, that there's some law governing motion of this pendulum. In fact, for those of you who are interested in history of science, there's a story about Galileo observing I guess it was some censer in a Catholic church that's like a perfume, not perfume, I don't know the right terms, but something kind of swinging back and forth, and he noticed that it seems to be swinging back and forth in an even time interval. He timed it using his pulse, and there's something that you can observe about motion of this object, even before you know a lot about mechanical details. You know a lot before you know a lot about forces, Newton's laws. Galileo came before Newton. And this is the starting place for our discussion of energy. Because, so while this object is moving back and forth, a lot of things are changing. I can actually plot things. Let me do a show plot and show you the dynamic things that are going on as this moves back and forth. You can see that its speed changes quite a bit. Its speed is 0 right here at the end of the motion, and then its speed is maximum at the bottom here. But as you look at this, there's kind of a sense of constancy here. It seems like this swinging pendulum is always coming up to the same speed. And I can also try to show Y position. When you look at the Y position, then as it moves back and forth, you see that it always comes up to the same height. It seems like there's some unexpressed law of nature that causes this pendulum to move in this very regular way. So energy is the concept that expresses that. In particular, energy as a conserved quantity. That when you look at the plot of how this moves, that the reason, the postulate or guess or whatever, the reason that there's this regular pattern, and the reason that this speed comes up to the same value every single time is because there's this conserved quantity called energy. And when this swinging pendulum comes to the same point here at the very bottom, then it has the same speed every single time because this quantity of energy is conserved, and it being conserved, you achieve the same value each time. So that's really the beginning place for the discussion of energy. This desire to, or this recognition that there is a conserved quantity, and this desire to express that conserved quantity. And now, one thing that's nice about having this simulation is that you can do certain things that that's kind of unrealistic to do with the real demonstration. In particular, here the speed always comes up to the same value, mainly because I cheated and I turned off the air friction or air resistance before I started this virtual class session. So if I turn this back on, then you will see that this pendulum doesn't always reach the same value. You can, over many iterations, you can kind of see it going down, it'll slow down to stop eventually. And you know, that's the kind of real world pendulum. But as we do with many things in physics, we first imagine an idealized scenario. And in the idealized scenario, in a world where air resistance doesn't exist, or maybe we do this in vacuum, then this pendulum has constant energy, constant mechanical energy. And this is a setup that conserves energy. So that's really the introduction to energy, that it's a conserved quantity. And that's probably the only kind of a working definition that we can give to energy, that it's a quantity that objects have and that it's conserved. So I'm just doing this for the first few minutes to illustrate some things. This is a really nice demo to bring in when we start talking about energy, because the idea of energy ties into really intuitive ideas that people have. And what we define in physics is an attempt at connecting those to those intuitive ideas. So let me just show one thing that illustrates where that intuition comes from. I'm just gonna pull off one of the bolts to the side and let it go. It's a fun, mesmerizing demo. And I think as you said, move, you can maybe imagine an ideal version of this. So, you know, this is real world with the air resistance, with the friction, with the whatever. So this whole thing comes to a stop eventually. But it takes long enough time doing that, that it's possible to imagine an ideal version where I let go of this ball, and this motion that you see in the first two collisions or so, that happens forever. Like, you can imagine that if we were to improve on it, make it perfect, that the first two bounces you saw can go on forever. And that's really where the idea of energy comes from, that there's a bit of some kind of conserved quantity that that persists in things like motion. And and we are going to be working with the mechanical energy in this class, mechanical energy being sum of potential and kinetic energy. And this is an illustration of mechanical energy. When I lift this up, that increases potential energy. That's energy associated, gravitational potential energy is energy associated with the height of this ball. And as it swings down, it gains kinetic energy, and the kinetic energy is transferred all the way to the other side, and this ball goes up with such a speed that it reaches about the same height as the original ball. And that's what someone could look at and say, oh, that's an illustration of conservation of energy. Now, as you look at this, there are some questions that might come up. But let me do a couple of demos first. So you saw the version with the one ball. That's not too surprising. Or maybe if it was, well, I think once you say it enough times, then it becomes mundane. So that's the demo with the one ball. Now, I want you to think about what will happen if instead of lifting one ball, I lift two balls and let go of them at the same time. Let me give you some time to think about it. And then I'm going to let go. Fun. So let me try that again. So two balls. And let them go. You see how two balls come out? And I think that that's something that I hope raises questions. So it's easy to understand that how if you have two balls raised to some height, then okay, they have twice the energy. But given that twice the energy, why does it have to be that it's two balls coming out with the same speed that they came in? Why couldn't it be that somehow all of the energy goes into one ball and this one ball comes out? Like this one ball goes to this height. Like that, I mean, so it's one of those things where with the conservation of energy alone, if you try to argue that it's not possible for just one ball to come out with all the energy, you don't have enough of a basis for saying conservation of energy somehow prevents that from happening. Conservation of energy allows energy to gather in one object instead of being distributed over multiple objects. And there's a saying in physics, it's most commonly said in particle physics, where there's a context for it that I'm not going to get into. I guess the short PT saying is, whatever is not forbidden is mandatory. I mean, referring to if you don't see something happening, so it's somehow forbidden, then the reason you don't see that happening must be because there's a law of physics forbidding it. So, if there was no law of physics forbidding it, then it would have been mandatory in that you would have seen it. It doesn't work in every context. It works in particle physics where there's so many events that if something isn't forbidden, you should see it some of the time, even the very rare events. So here, what I want to propose here is that there is some law of physics forbidding that when I let two balls swing down, there's some law of physics that forbids only one ball from coming out. Some law of physics that dictates that two balls must be coming out. And we are not quite getting that far this week. That law of physics will have to wait until next week to cover that properly. Let me just to wrap this up with a couple demos. So you have seen this with one ball, with two balls. Now I'm going to pull out three balls, and I want you to think about, hey, how many balls are going to come out when I release three balls at the same time? So okay, when I release three balls at the same time, how many balls will come out to the right side? Give some time to think. And then let's give it a try. Three balls come out. When I do this in class, not everyone, or maybe less than half the class guesses, if they haven't seen it already, less than half the class guesses correctly that three balls will come out. I mean, makes it sense. I mean, in the motion, what it is that the middle ball doesn't really get affected all that much. It's just going. But yeah, three comes in, three goes out. Nothing prevents three balls from going out. Let me try four balls now. Difficult to do from side. Okay, I got four balls. Let's see. Four ball comes out. I think once you see the version with the three, then the four is not as impressive as it could have been. Now, the last demo, what if I let 5 volts come in? Then 5 volts goes out. It's very boring. Perhaps the boringest of all. So this is Newton's Cradle, and it's a quite fun demo. I, I guess it's more of a demo than I don't know if there are interesting physical problems we can solve with it. I guess there are some elastic collision questions you can consider next week. But yeah, so this is the demo. So that's the long-ish introduction to energy. It's really the concept of energy comes from this observation that in nature, as you observe motions that are common in nature, that there appears to be a conserved quantity. And the reason we talk about different forms of energy is to, out of this desire and need to quantitatively express this property of things that appears to be conserved in nature. So when you look at energy, it's always a calculated quantity. Kinetic energy is a calculated quantity. Potential energy is calculated quantity. And as you will see in this video, as part of pre-lab, it talks about thermal energy, chemical energy. All these are calculated quantities. What I'm trying to say is there's never a situation where you measure energy directly. This is in contrast with other physical quantities. Other physical quantities like velocity, position, those things are directly measured. But energy is one that will always be calculated from other quantities that you did directly measure. So having said that, the reason I'm emphasizing this, that it's a calculated quantity, is so it's a kind of a matter of definition. So with the kinetic energy, we say that kinetic energy is equal to 1/2 mass times velocity squared. And you could ask a question, why is that kinetic energy? And your answer is that, well, turns out as things interact in an elastic setup where kinetic energy and potential energy, where mechanical energy is conserved, this expression is the expression that's conserved, not mv squared, not m times v, although that will sometimes be conserved. So that's why this is the expression for kinetic energy. And the expression for potential energy, you will see two different forms of potential energy. Well, technically three. Well, you'll see two different forms. You'll see gravitational potential energy, and you will see spring potential energy. And the reason we come up with the expression for potential energy that we do come up with is because those expressions lead to the total mechanical energy conserved in situations where there's no involvement with the thermal or chemical energy. And later on in future classes, when we talk about thermal and chemical energy, that will still be with the goal of conserving this quantity that we call energy. So with that, I need to mention a few more things that's not listed here, because when you eventually go up to physics 4C, you will see other forms of energy. So the other forms of energy that I just want you to mention now are radiative energy or radiation energy. That's the energy carried by light, energy carried by electromagnetic radiation. And one particular form of energy is, I love highlighting this because it's the form of energy that most people don't anticipate. It's what we will call in physics 4C, rest energy. And it might sound a little bit odd, especially in contrast to kinetic energy. I mean, so it makes sense that moving things have energy. But what do we mean by rest energy? You might have heard this phrase before in popular science and whatnot. E equals mc squared. And as a matter of general expression, that's not correct. What it's referring to is rest energy of an object that has mass m is mc squared. And in special relativity, you will eventually see this expression that total energy is equal to gamma mc squared. And gamma is a numerical factor you will see. And in special relativity, kinetic energy gets rewritten this way. Instead of it being 1/2 mv squared, which is only classically correct, not correct in special relativity, kinetic energy is the total energy minus the rest energy. And when you get to physics 4C, you will see the derivation that motivates all these new expressions. And what I want to highlight is that our underlying motivation in defining energy is to describe a conserved quantity. And in special relativity, the reason we have to start describing rest energy is because unless you do that, you see energy changing. You see a massive particle that's decaying into two very fast moving particles, or you see two highly energetic particles colliding, forming one thing that's massive, and so mass is changing and it's at rest. So if you're just looking at kinetic energy has changed. And in order to, in that context, to still hold to the kind of postulate, assumption, law that energy is conserved, we have to modify our definition of energy so that it's a conserved quantity. It's a little bit backward, but there's a good justification for it. And it turns out when you introduce just a few things, then everything still works out right. So, but I guess when you see this, I didn't want you to feel like we are arguing in circles, because really the starting place for energy is that it's a conserved quantity. So I guess the moment when we can no longer modify our definition so that energy is conserved, then that's when physics breaks down. But that hasn't happened yet. So this is a topic that we kind of skimmed over way back at the beginning of semester when we were covering chapter 2. So in chapter 2, we talked about vector algebra, or more precisely, we introduced the vectors. This might be first science math class where you've seen vectors, and even if it wasn't the first, really no other class emphasizes as much on vectors as physics class does. So at the beginning of the semester, we introduced the vectors as an arrow-like quantity that has a magnitude and direction, and we talked about vector sums and vector differences, or I guess that's one part of the vector algebra. So we talked about how if you have two vectors, you could add them algebraically. You break them down into components, add them component by component, and that gives you the sum. And we also talked a little bit about how you can add vectors graphically, the head to tail method that gives you the resultant vector without needing to refer to components. And this geometric representation of the vector, that is something that we really do focus on, and it's important in understanding of physics, conceptual understanding of physics as you go to higher levels. We talk about coordinate independent representation and whatnot, and that kind of coordinate or the axis independent way of describing things, it really needs a mathematical object like a vector that exists independently of x and y axis that you might define. Now, chapter 2 actually covers more things about vectors that we kind of skipped on back then. All of that is in section 2.4, product of vectors. And today I want you to cover one half of what's in section 2.4. Because in section 2.4, it covers two different types of products. And for today, I want to spend some time talking about the dot product. So your textbook section actually does contain mostly everything. So what I'll be lecturing on now will be more or less duplicative of what's in the textbook. So if you already read through the textbook, then great. What I say now in the next 5 to 10 minutes should be something that you already know, which is great. And this section also talks about a vector product, which we will reserve for about 3 weeks. We'll do the review of vector product or cross product when we need them. We are going to need them as we talk about rigid body motion. So with that, I will just do our coverage of the dot product. So that product is it's a way to multiply two vectors, and I guess in the simplest description, you imagine there being two vectors, let's say vector A and B, and there might be some situation where you need to multiply these two vectors. The context that you will see as we go through chapter 7 this week is we are going to be defining work as a product of force times displacement. And the thing is, force and displacement both are vectors. And vectors are more complex mathematical object than simple numbers are. Numbers like real numbers or even complex numbers, the scalars, you know how to multiply them. That's kind of what you learn in algebra, what you learn in college algebra or pre-calculus, or even before. Once you have objects that are vectors, the fact that they have direction is an important thing, and that causes potential either ambiguity or it's something that you need to address and define your operations precisely with respect to. So it'll turn out this kind of product defining work, it'll be defined through a dot product. So since this is essentially a new algebra operation for us, I should just define it the way we define multiplication through multiplication table, and we define division, and we define addition, subtraction. So we should define dot product. This is a new binary operation. It takes two inputs, vectors A and B, and then it spits out an answer. And with the dot product, the important thing about the answer that it spits out is that it's going to spit out a scalar answer. So sometimes we call this scalar product, which is super confusing because there's also multiplication by scalar coefficient, which is not the same thing as dot product. But sometimes people do call it scalar product. You might also see the name inner product that has some other reason for it. I'm not sure. We will most of the time stick with the name dot product. And that refers to how we write this product usually. We write it as vector dot, center dot, with another vector. And this center dot has a different meaning from when you are just writing down, I don't know, x dot y. And when you do something like this, usually dot is there to replacing a multiplication symbol. And sometimes you can even omit it. Like none of that is a big deal. The biggest thing about this dot in the dot product is that you should never omit it. Like if someone wrote something like AB, this is an error in mathematical notation. And when you see a physicist to say something is an error in notation, it's serious because we are known for abusing notations. This is the kind of abuse that even we wouldn't do. So in a dot product, when you multiply these two things, you are going to get a number. You are going to get a scalar. You are going to get some much simpler mathematical quantity that doesn't have a sense of direction. And this is how the dot product is defined to give this a scalar number. So because you are multiplying two quantities that have a sense of direction, so you need some way of characterizing those directions. And the way we define this, only the relative direction between the two vector matters. So there's an angle between the two vectors, called that theta. Then the product between these two is defined as the magnitude of the two vectors, which are scalars, so we know how to multiply them already. So the product of those magnitudes of two vectors, and then we multiply by cosine of theta. And you might ask, why cosine? Why not sine? Why not tangent? And it's a definition. I don't have to give a justification, except to bring this into alignment with maybe another definition that you might have seen. So this is what I like to call physics definition of dot product. And if you have taken math classes where they do cover something like a dot product or maybe an inner product, you might have seen a different definition of dot product. So I remember in my math classes, I've seen this. If you have A vector dot product with B, then the dot product was the product sum of the product of the component. So you would take the component AX, BX, multiply them, add it with all the other dimensions. You have typically X, Y, Z, 3 dimensions. And this would be presented as the definition of that product, unless that's what I remember in math class. And this is the component definition of that product, or I guess the math definition. And there's a reason I'm drawing this distinction here. I've called this the physics definition, implying that we physicists prefer this over this other definition that some other people prefer. And the reason for it is it has to do with whether you have to define a coordinate axis. So when you look at this definition here, nothing here requires that you define a coordinate axis. If you have two arrows, you can measure the angle between them using whatever means you have, and then proceed with this calculation without ever defining a coordinate axis like this is my x, this is my y. You don't ever have to do that to apply this definition. When you look at the component definition, well, the word component already implies that you have already found some axis or some basis that you are going to break down your vectors into. So even writing down of these components implies that you have defined an axis. Now, it might be that you could just choose any axis without loss of generality, as in having chosen this axis doesn't actually affect the dot product. But this definition doesn't really make it clear that that is indeed the case. So, so in terms of how we define the product, we prefer to define it this way. Now, what I can do, and the reason for this lecture is let me give you the justification for using this as our definition of or rather, let me show the equivalence between the physics definition of that product and the math definition of that product. And in fact, this is another reason we prefer this instead of the other one. Proving this implication is actually a lot easier. It's much easier to start from the physics definition and then show that if this is true, then this is also true as well. Going the other way, I'm not sure if I can do that now. I'm sure there's a way, but it's a lot harder, so I'm not going to. So let me use this as a starting point and show that if you adopt this as your definition of that product, then in our three-dimensional Euclidean space, that implies this component by component version. So the way to do it is to write these vectors in their component form using unit vectors. So you might write A in the in terms of the unit vector decomposition of A. So if you imagine here, there's I have a x hat unit vector, y hat unit vector, and you can describe it as scalar multiple of x hat. Um, that's the x component plus some scalar multiple of y hat, and those will be the components. So I can write the vector A that way. So x component times the x hat for the x direction plus the y component times the y hat for the y direction plus g component times the g hat. So this is the kind of writing that you can only do after you have defined your axis. And even though you don't see a g axis, you should assume that there's a g axis somewhere. And I can do the same thing with vector B. So bx, x hat plus by, y hat plus bg, g hat. So those are our two vectors. And I guess I should just do the product. This is the product I have. Let me just multiply a and b. And I hope you will be a little bit I hope there's a little bit of confusion, like multiply. How do you multiply vectors? Because it's that kind of wonderment is a sign of mathematical maturity, which is part of which ought to be taken care with any new mathematical operations that you see that you haven't seen before. Because you shouldn't draw assumptions about what this dot means if you haven't seen it before. So let me just write it out first, and then I'll make a claim that I won't prove, but I can honestly claim is true almost all the time. So let me just write it out. I'm just replacing A with the expression for A I have here. So I have that dot product with B. And the first question you should have is, once you have this that expression, like what do you do with this product? And this is a bit of an assurance I can give. There's a reason they call this dot product, not dot summation or dot something else. In algebra, the two basic operations are additions and multiplication. And when I say the word multiplication, it covers much bigger groups, bigger things that you will maybe see in abstract algebra or upper division level algebra classes. One of the properties that this is one of the care that mathematicians take when they propose a new operation that they're going to call product or have some association with the sum. They make sure they obey certain properties. So you might have heard of things like associative property. I think associative property is something like if you have A plus B plus C, then you could do either A plus B, then C, or you could do A plus B plus C. And you might have heard things like commutative property. That's another one. And there's and here's the one biggest one that relates to things that we describe as addition with the things that we describe as multiplication. It's the distributive property. It's one of the few algebraic properties that you might have heard about that involves both addition and multiplication, like this associative property. Addition has that property and multiplication has that property, but it's like describing what that one operation does. But when you have a distributive property, that's a property that describes how multiplication interacts with summation. So it's something that you maybe haven't seen before. If you have A times B plus C, then it's equal to A times B plus A times C. that when you have multiplication, you can distribute it into the things that are connected by summation that it's multiplying to. Like this kind of operation, you've done it many times with the mathematical objects that you are already familiar with. And what I'm telling you is that when mathematicians call something a product or multiplication of any kind, they should obey this distributive property. Unless this particular operation had that property, they wouldn't call it a product. They wouldn't call it a multiplication because it would be super confusing. So with this new operation and this new issue object, we can rely on this distributive property to simplify, to expand the things, expand it out, and to rewrite it in a way where we feel like we now can do something about this product using the definition that we have. So let me distribute. When I distribute, I'm going to have 9 terms. I guess let me write it all out. So I'll just be writing silently those 9 terms that goes from multiplying ax with the bx. So I have ax x hat times bx x hat plus ax times by. So that's the pattern. Now I have ax x hat multiplied with bz g hat. Okay, let's keep going. So that's the 3 of the 9. The other 3 will come from ay, and then the remaining 3 will come from az. So I just have to write these out. Ay, y hat. Many of them will go to 0, but I think it's instructive to see all the terms, even the ones that will go to 0. Because I think if you have never seen the terms that vanish, then you haven't had a chance to learn why they vanish. Okay, plus y hat times bt t hat. Okay, one more, and we'll be done. So this is gonna involve the g component of a, and then all 3 components of b. And note how I'm always putting that dot because with the dot product, it's not an implied multiplication. You have to explicitly write the dot, otherwise you've missed something important. All right, so that's the expression with the 9 terms that we are evaluating. Now, I'm going to just say and appeal to some properties that I think we all agree that they have. One is the commutative property, meaning if I swap this order of these 2 things, then it doesn't change anything. Like if I swap, if I wrote somehow x hat ax, like that, it's still scalar. It's a scalar multiplication, or it's a multiplication by scalar. So where you put the scalar doesn't matter. That's one. And so, in fact, as an example, like here, I could rewrite this as ax bx times x hat dot with x hat. This would be an allowed operation because of commutative property of the scalar with the vector and in multiplication. And when you look at this definition of the dot product carefully, although I don't need that property, so let me not invoke it. With the dot product, the dot product also commutes. If I have x dot x hat dot x, or a dot b is equal to b dot a. It's a true property, but I don't think I need it, so let me not invoke it. Okay, so using that commutative property, I can simplify all of these terms in terms of what happens with the dot product of the 2 unit vectors. So if you have x hat dot product with x hat, there is something I can simplify based on the physics definition of dot product. Product of magnitudes 1 times cosine of the angle between them. If it's the vector with itself, angle between them is 0. So cosine of 0 is 1. So this dot product is 1. And you have x hat dot product with y hat. And when you do x hat dot product with y hat, you see, okay, the product to the magnitudes is 1. And cosine of angle between x hat and y hat is 90 degrees. They are perpendicular to each other. So cosine of 90 degrees is 0. So this dot product is 0. And you will see the same thing with the x hat dot product with the g hat. This is the same thing for x hat dot product with the g hat. And for the remainder here, essentially what you will see is that when you have a dot product of unit vectors, if it's the one and the same, then it's going to be 1. That will be true for y hat dotted to y hat or g hat dotted to g hat. And for any other combination that mixes x with y, y with g, you are going to get 0. So for any other combination, you will get 0. And that gives us our vanishing terms. This product is going to go to 0 because the dot product goes to 0. This is going to go to 0. And this is going to go to 0, y hat dot to x hat. Okay, this one will survive. This will go to 0. This will go to 0. This will go to 0. And this will survive. So out of the 9 terms, you only have 3 remaining terms. And those 3 remaining terms are ax times bx plus ay times by plus ag times bg. And this is the component by component description of that product. And this might have been given to you as the definition of that product, which is fine. These two definitions are equivalent to each other. So you can start from one end and get to the other end, vice versa. But I find this direction to be a lot easier. And one last note, you are going to see this more, this is something that's more useful in more abstract math classes, but I think it's worth pointing out. This placement of cosine theta, it becomes a very useful way to define angle, particularly in situations where it's hard to imagine the angle in a physical space. So, in 2 dimensions, you can see the angle. It's not a big deal. So this is not something that's super useful or appears to be useful. But this is something that's useful when you are starting to deal with a 3-dimensional space, because sometimes when you see the angle, when it's rotated in some way, then it becomes harder to take a projection and whatnot. And it's something that becomes essential as you deal with higher dimensional vector spaces in upper division math. So you have this equality that this numerical value for dot product should be equal to this numerical value for dot product. The magnitudes of the vectors times cosine of theta. And using this equality, you can do an interesting thing. You can solve for cosine theta. And when you solve for cosine theta, this is what you get. Cosine theta is equal to sum of I going from 1 to 3, ai, bi. That's the dot product component of the description of dot product, the left-hand side, divided by the product of the magnitudes, a times b. And so this, in some sense, it gives you a way to define angle, theta, particularly in context where it's not immediately clear how to represent the angle. So in the context where we are introducing this dot product, two-dimensional vectors, this seems kind of silly. You can just measure the angle. But this idea of quote-unquote angle is something that becomes more useful in more in more abstract linear algebra context. So you'll probably see that in the future. I just want you to highlight. I think there was one homework set in week one where the yeah, I remember doing this in virtual class session. There was one thing that was asking about angle between two vectors in three-dimensional space, and this was the way to quickly do it, because once they've given you the components, dot product is super easy to compute, and you can compute the magnitudes, and from that get the angle. And it's one of those things where if you're trying to visualize it, then it's hard. When you do algebra is a lot easier. So yeah, I think that's the comprehensive coverage of that product. And again, we held off on this until now because now is the time when we need it to describe work. We define work done as a dot product between the force. So this is the work being done by this particular force. That's a force dot product to displacement. Both are vectors, and the way we define that product, it'll give us a scalar. So work is a scalar quantity, and this is the first time when we really needed that product to describe some physical quantity that we are interested in. So here we are. And yeah, and there are other ways to describe that product. Sometimes this can be described in terms of projection. So you can imagine taking projection of f along the delta x as described by f parallel to delta x times the delta x, or the other way around, f times the component of delta x that's parallel to force. That's so both of these descriptions come down to matter of which of these two magnitudes are you associating this cosine theta with, because you could describe this as the projection of b onto the direction along a, or if you had a times cosine theta, you could describe it as projection of a along the direction of b. So, okay, I think that's the last thing I need to say about that product.